Okay, so cylindrical shell method. Here's the idea. Suppose you have a shape that looks like that, and you're going to revolve it around the y-axis. There's a problem that results. If we take this and revolve this around the y-axis, I get a shape that something like that, correct? And now, yep, Bo sees the trick right here. Don't draw this. If we do the washer method and you draw the rectangle like such and you rotate it around, you can see that we have a problem with the resulting region. And the problem is that the inside radius, the little radius, is the same as the outside radius, right? The inside radius is corrected by, created by f of x. The outside radius is also created by f of x. So therefore, if you did pi times r squared minus r squared, they would cancel each other out. So the washer method does not work in this scenario. So we turn to another method. And the method that we choose is the cylindrical shell method. And what that does is anytime you draw a rectangle where the top and bottom is the same function or the left and right is the same function, we have to choose another method. So what I'm going to do is I'm going to draw a vertical rectangle. So how would that do anything? Well, if I simply just rotate that around to the other side, I get a cylindrical shell. So some people think of these in different ways. Some people think of those little dolls that you take them over Christmas time and you put it nesting dolls. Yeah. So same type of scenario. If I were to, say slice it right here instead, you could see that this shell Yep. Yep, it's empty in the middle. Okay, so here's, it's this. You're thinking pasta shells. Okay, wrong class. Okay, look, see, this is a shell except it has a bottom. And we could put another, I mean, you could conceivably get another water bottle that's just like, say, a centimeter smaller in radius. Casing, yeah. So if you watch any, like Law and Order, and they find a, they find a shell casing from a bullet. So that's what we're seeing, and you can stack an infinite number of those around themselves so that they continue to expand and grow and cover that whole region. So we got this, or it's really like a label around a can. It's something very, very thin, okay, very, very thin that wraps all the way around. And you can continue to create more and more of those. What we do is we unravel it. We take the shell and we unravel it. This width right here of this rectangle that you originally created in both situations is dx. So the width of this label that we've unraveled is dx as well. I'm taking one of these shells and I'm cutting it right down the middle and unraveling it so it makes a rectangle because I need to find the volume of this thing. So now I've got a rectangle. That's easy to find the volume of it. A rectangle with a little bit of thickness, a prism. So we have a height that is established by f of x. F of x gives us the height. Yes. Yeah. Yes. All right. And then how do we compute the length of the rectangle if we unraveled it? It's the circumference, which is 2 pi r. Now, the circumference is really important, or the radius is really important to identify. Let's suppose that your bounds were from 0 to 5. Your radius continually changes, doesn't it? I mean, in one situation, your radius is right there, and then when it's the red one, your radius is right there. Would you agree that your radius has to be somewhere between 0 and 5? And that's, we're integrating x with respect, we're integrating with respect to x. So simply these radiuses are just whatever x value sits between 0 and 5. So a lot of times it's just an x that goes in there. But suppose instead of rotating around the y-axis, suppose you're going to rotate it around 6. Then your radius would be 6 minus x. You do right minus left. Right now you're doing x minus 0 and you're getting x. So we'll do an example like that and you'll see it. So volume for, or formula for volume by cylindrical shells, we simply do 2 pi times the integral of, so I got my 2 pi times my radius times my function, and I integrate from a to b. Because 2 pi r times f of x times dx is the volume of that shape, right? And I do an infinite number of them. Okay, so let's do the classic example, see how this works out. We have a task to find the volume of the area bounded by y equals 2x squared minus x to the third and y equals 0 revolved around the y-axis. So y equals x squared times 2 minus x, and y equals 0 revolved around the y-axis. I could see that this shape as a cubic, I could see that this shape is a cubic. It has x-intercepts at 2 and a double root at 0, correct? So as I graph this, it's going to look identical to what I drew up above. It has a double root of 0 and then passes through 2. It continues up that way, but we won't draw it because it's also bounded here. So this is the region that we're focusing on. So if I rotate it over, that's what I have. Can't draw left to right because left to right is the same thing. So washer method does not work. So therefore, I select an x value. And at that x value between 0 and 2, I draw a rectangle. Does that have width of dx or dy? Dx is the width. I rotate it around the y-axis. And I get that shell, or that casing, as you said. Yes. You're thinking of anytime we rotate something, we get something symmetrical. You're thinking of area. We can do the area from here to here and double it, but we're trying to find volume, and so that's why we do this 2 pi r type thing. That creates the other side of it. Okay, so let's unravel it. What is the width of this rectangle? Dx. What is the height of the rectangle? 2x squared minus x to the third. I am revolving it around x equals 0. What's the distance from x to x equals 0? X. So my radius is x, so 2 pi r, or x. Therefore, the volume of this piece is the quantity 2 pi x times 2x squared minus x to the third dx. I integrate 2 pi. I'll distribute my x through. 2x to the third minus x to the fourth dx. What are my bounds? 0 to 2. 2 pi times x to the fourth over 2 minus x to the fifth over 5. 2 and 0. 2 pi times 2 to the fourth is 16, divided by 2 is 8, minus 32 over 5. 8 is 40 over 5. 40 over 5 minus 32 over 5 is 8 over 5. Times 2 pi is 16 pi over 5. Obviously, the setup is the critical part. Okay. Try one that's much more complicated. This one, y equals x minus x squared. So that's y equals x times, whoop. Yeah. It doesn't. All right. Kitty, you want to pop your head out and tell Miss Nelson about her treats? Or Marcus? Okay, so this one is different. We have an upside down parabola that goes through 0 and 1. It's bounded between the curve and y equals 0. So I have that area. And we're going to revolve it around what? X equals 2. That's my axis of rotation. Not there? Huh. Oh. Okay. So, when I revolve it around, this point that's at 0, when you revolve it around 2, it will end up over at 4, and 1 will end up at 3. So we have that shape. Okay? Kind of like a donut. Half of a donut. Bagel. Half of a bagel. There you go. All right? That's what Emerald was thinking. All right. Wow. Okay, so there we are. No, no. No. Watch this, okay? Take that. Boom. We slice. Okay, we can't draw it sideways because if you drew it sideways, the left and the right would be the same. So you can't do a washer method here. So we select an x value, so the thickness is dx. And you rotate it around Okay, and you can see the shape that I get. So what I need to do now is I need to unravel that. Yeah. So we've got dx is the thickness. What's my height? X minus x squared. What's my, I got 2 pi r. 2 minus x. You do the distance, so the radius is the distance from here to there. That's your radius. And that distance is 2 minus my x value. So therefore, the volume of that piece is x minus x squared times 2 pi times 2 minus x times dx. It's the volume of a single slice. I do an infinite number of slices. 2 pi from what to what? 0 to 1. Your original area is how you bound it. Good. Let's distribute negative x squared times negative x. X to the third. I have a negative 2x squared, and a negative x squared makes negative 3x squared. And I have 2 times positive x is 2x dx. Got my integral. 2 pi times plug in 1. Minus 1 plus 1 cancels. You may not write 90 degrees. That's a joke that you probably get to use only a couple times in your life. You know what I mean? You're standing in calculus class and pi over 2 comes up, and obviously we're not, I mean, in pre-calculus class, they would say, well, yeah, what's wrong with pi over 2? It is 90 degrees. They don't, that's the only way they equate it. Now you guys equate it also to volume and stuff. So, good, good, good. Circle of life. There you go. Okay. All right, last example. Find the volume of the area bounded by y equals x squared and y equals x revolved around the x-axis. There's y equals x squared, there's y equals x. I'm going to revolve it around the x-axis, it says. Now, would I be allowed to just use the regular washer method here? Yeah. However, I'm going to choose to use the shell method. What? No. No. Oh, yeah. Sorry. There you go. All right. So, okay. So, to Sini's point, this one's interchangeable. Shh. This one's interchangeable, washer or shell. But it is not the case where all the washers you can do shell. It's not the case where all the shell you can do washers. And some people were concerned third hour saying, well, how do we know which one to do? The key lies in how you draw your rectangle. Can you draw a vertical rectangle? Yes, so you could do a washer and integrate dx. However, can you also draw a horizontal rectangle? Yes, because the right is different from the left and the top is different from the bottom the whole time. So I could do dy and integrate with a shell. And that's what I'm going to choose to do. So I actually, I'll be honest, one reason I really like the shell method is because you don't have to square everything, right? And sometimes squaring everything becomes very difficult. For example, the last problem in your study guide, you can use the washer method. Go ahead. It takes forever. I think I've only had a couple people who've been able to do it without making a mistake. Okay, go ahead. I'm just saying that there's a lot of times where the shell method is a nice method. So as I do this, rotate it around because I don't like to square things, whatever the reason might be. Get this shape. What's my thickness? dy. Because my rectangle had vertical thickness. So I've got dy. What is my, what's my height? Two pi y. 2 pi y. And then my length across the bottom is the distance between these two. Distance between these two is that length. X squared minus x. But I need to be in terms of what variable? Y. So instead of y equals x squared, it will be x is square root of y. And instead of y equals x, it's x equals y. There you go. So the volume of one of these pieces would be 2 pi y times y to the 1/2 minus y times dy. You want an infinite number of them, so 2 pi y to the 3/2 minus y squared, integrated from 0 to 1, yep, because the y value, these intersect at 1, 1, which you guys saw. So the intersection is at 1, 1, so the y value is 1, and then it drops down here to 0. Good. I distributed the y through. dy 2 pi times, what's the antiderivative of y to the 3/2? 2y to the 5/2 over 5 minus y to the 3rd over 3. Plug in 1, 2 pi times 2/5 minus 1/3, or 2 pi times 6/15 minus 5/15, 1/15, so 2 pi over 15. Awesome sauce. You weren't really proving anything, you know, in order to be a proof. If it said prove that the volume of that was 2 pi over 15, then you would. All right. I've got just 4 problems to practice on this. They take a little time. It's a little bit getting used to, but I believe in you guys. I know that you can do it. It's your last homework assignment for this unit. Right now, the plan is half the tests on Wednesday, half the tests on Thursday. Monday and Tuesday will be full work days on the study guide. Study guide key is already up and posted. After this unit, I know it sounds crazy, you guys, but after this unit, you guys will have for sure one more test.